Okay, so in this video I want to talk about imaginary lines in geometry more. I want to talk about how you can connect up imaginary points, and I want to talk about how you can find the tangents from a point inside a circle to that circle. This is something which requires imaginary elements. So let's just recap. We have a real line, then imaginary points on that line, a pair of conjugate imaginary points, can be represented by an elliptic involution. What an elliptic involution is it's an involution that can be specified by two pairs of mates. So we have the red mates here, they get mapped to each other. Whoops, red mates there. And we have these two here which are green mates. They get mapped to each other under this involution. Remember that an involution is just a period 2 projectivity. It's a projectivity which returns every point to its own position if it's applied twice. So in general, an involution can be specified by describing two pairs of mates. We say a pair of points are mates with each other if they get mapped to one another. And an elliptic involution is where these pair of mates separate one another, as shown here. So given such a thing, we basically have inferred here this pair of conjugate complex points. This is mostly the subject discussed in the last video. They appear as the fixed points of this involution, essentially. Now, imaginary lines, just as imaginary points, go together in conjugate pairs and they both are sort of carried by a real line. So imaginary lines are carried by a real point. So let's say this dark blue point here is the carrier. And we're going to construct imaginary lines now by linking this point with these imaginary points. And to do that, all we do is draw a line through our dark blue point, linking to each of our object points and image points that describe the involution of the line. What this gives us here is an involution of the elements of this point, an involution of the lines through this point. So I'll colour in the lines appropriately. This line is red. This dotted line is the mate of the solid red line. We have a green line and a dotted green line that's the mate of the ordinary green line. So we have two pairs of mates of lines that separate each other, and this is precisely how an elliptic involution of lines is specified. Okay, so let's fill out this involution a bit more clearly. We'll start by examining this involution of points on the line, and if we determine the centre of rotation that generates this involution, well, with a couple of perpendicular lines through this centre, we can basically find new points corresponding to this involution. Now joining these new points with lines through our dark blue point, this gives us a variable line in its involutory mate. Under this elliptic involution. So now there's something which I'm not going to make an argument for, but it's a fairly important fact about elliptic involutions of lines through a point. Okay, so there are two possibilities when we have an elliptic involution of lines through a point. In a very special case, as is going on with this green point, we have that mates are always perpendicular to each other. But that's only a very special case when we happen to choose a point which happens to be the sort of point of rotation. The much more general case is that there's just going to be one pair of mates which are perpendicular to each other in the elliptic involution, and no others. So we can see this happening here. We just have this one scenario around here where this yellow line and its mate are perpendicular, and in all the other cases of this elliptic involution, that's not so. Okay, so let's return to considering these imaginary elements. As I was saying in the last video, this sort of setup can be thought of as a kind of imaginary triangle, or let's say complex triangle. We have two conjugate complex points on this real line, and they are joined by complex conjugate lines through this real point. So that's two lines through the point connected to 2 points on the line. That forms a triangle. Now we're going to have a look at the interesting question of how do you construct tangents from a point that's interior to a conic. And we'll see that that also relates to these kind of complex triangles. Suppose we have a conic and we have a red point which is interior to it. Let's say we also have a blue point which is the centre of the conic. Now I'm going to show you how to use imaginary geometry to find tangents to the conic from this red point. And what this actually is, because the tangent of a conic is the dual concept to a contact point of a conic, in the sense that you get it by swapping around the roles of lines and points and so on. So basically what I'm going to show you is you can get it yourself if you want to pause the video and have a go, by dualizing our construction of the contact points of a conic with a line which doesn't have any real points in common with it. So anyway, let's go on and show this construction. So you begin by joining your point that you want to find the tangents to via a line through the centre, and then you draw a line that's perpendicular to that one. Those two lines are going to meet the conic at 4 points, and if you draw in the extra lines you can draw between those 4 points, those are going to determine 2 more points of the diagonal triangle of this quadrangle. And now simply, if you draw lines through our initial point, you now have 4 lines, and those 4 lines give you the elliptic involution of lines through this red point that correspond to the tangent lines through the point we're interested in. And so this gives us a description of the elliptic involution corresponding to these imaginary tangents, but it's also represented here in a unique way, because we have the two mates corresponding to the blue lines, they're mates with each other, they bisect, those two lines bisect the orange lines, and the orange lines are perpendicular. So this is sort of actually a canonical representation of these imaginary lines, in the sense that this is like a unique form of these imaginary lines. Also, there's something fairly interesting to note here, and that is that if we join these 2 points here, where these purple lines meet, if we had a black line there, well then you should see that this is actually exactly the picture that we got when we were trying to work out what the contact points were of a line, the black line, meeting the conic. So this is actually a self-polar triangle, because if we just work out now, where does this black line meet this conic? Well, the construction is basically already there, and we find that these 2 black points on this black line, they give us the amplitudes of the complex meeting points of this conic with this line. And so we have a real line with 2 imaginary points on it. I'll just colour in this real component of these imaginary points in green. So we have this real line with these 2 imaginary points joined to this real point with these 2 imaginary lines, the tangent lines through the conic, through this red point, and through this black line, the contact points of the conic. So this is actually a self-polar triangle. Okay, so now let's move on to another really fundamental thing about dealing with these imaginary elements, and that is, if you're given 2 imaginary points, how do you find a line through them? Well, if those 2 points are conjugate to one another, then the only line between them is the real line that's carrying them, and in that case it's obviously easy to do the problem. But what about more generally? Well, more generally, there's still just one line between a pair of imaginary points, but how do you find it? So here we have a scenario where we have 2 black lines, one of which is carrying the imaginary points A and B, and one of which is carrying the imaginary points C and D. Now, I've associated these imaginary points with directions because they're conjugates to one another, and so we can think of them as sort of 90-degree rotations in different directions, and so corresponding to the 2 different types of movement on this line. Now, both of these pairs of conjugate imaginary points are also represented by a real point, a real component, and an amplitude, and that's what these semicircles are representing. O' is the real component of imaginary points A and B, and the semicircle represents the amplitudes, the size of the imaginary components of those points. Similarly, P' represents the real components of the conjugate, well, let's say imaginary instead of complex, imaginary points C and D. Imaginary and complex, I'll use those terms interchangeably here. Okay, so it makes sense to leave these points coupled up. So we're not going to specify whether we're joining A to C or A to D or B to C or B to D. We're just going to say that we're going to join the complex conjugate points A and B to the complex conjugate points C and D. So we're actually thinking about how to draw lines from one pair of connected points A and B to another pair of connected points C and D. So what we're actually doing here, as you shall see later, is completing a quadrangle which has 4 of its vertices as imaginary points. So how do we do it? Well, we want to draw imaginary lines that go through these points, and basically to do this we want to find involutions of lines which are projective to both of these involutions of points, the one representing A and B and the one representing C and D. So to do this, note that the involution on this AB line is basically corresponding to a 90-degree rotation about O. So what we're going to do to begin with is to find the mate of X under this involution. X is the place where these two lines meet. So if we just make a perpendicular to the line from O to X, we find that the mate of X under this involution is Y. And we're going to do a similar construction on the other line. We find that the mate of X is Z. Now what we want to do is we want to find a perspectivity from the AB line to the CD line, because once we've found that, we're going to be able to find these involutions of lines which are common to both of these two involutions of points. So under our perspectivity we want to be sending X to X and Y to Z. But let's also find some more points. If we bisect these two green lines at the top, we're going to find 2 other involutory mates, and they're going to be harmonic with X and Y. So we'll call those points U and U dash, and we'll do similar on the bottom line, bisecting the green lines to find V and V dash. So we have 4 points on the top line and 4 points on the bottom. They're both harmonically related, interrelated with themselves, and so there's going to be a projectivity from one to the other, and that projectivity is going to translate X to itself. So it's going to be a perspectivity. So we've found our perspectivity. If we just join U dash with V dash and U with V, that gives us a point down here. And we'll call that point S, and that's actually going to be the real carrier for imaginary lines which are joining these imaginary points. But the story isn't finished yet, because we could have equally chosen v dash as v and v as v dash. We could swap round the roles of those 2 points, and then we'd have a setup like this, where u is in perspective with what's shown as v dash here, and u dash is in perspective with what's shown as v here. And that will give us another point, t, which could also potentially be a carrier of these imaginary lines. So what we've found here is that there are 2 different pairs of conjugate imaginary lines which can be thought of as joining up these imaginary points. So how can we think of this? Well, we can think of these lines through t as the line BC and the line AD, whereas we can think of these imaginary lines through S as the line BD and the line AC. So if we just look at these lines through S, drawing these other 2 lines in, we now have 4 lines through S, and what these are describing is an elliptic involution of the lines through S. So you can check for yourself that this same involution, which has a pair of mates as the cerulean blue lines and a pair of mates as the yellow lines, is induced by either the AB line or the CD line. It's common, and similarly you can make such a pair through T. So we have our 4-point construction. It's got 4 imaginary, it's basically a complete quadrangle. It has 4 imaginary points, and it has 2 real lines, and it has 4 imaginary lines. And then these 3 points, S, T and X, they form the diagonal triangle of this quadrangle, and they are all real points. There's obviously a tremendous amount more to say about this geometry of imaginary elements. My main aim in these 4 lectures has just been to introduce the constructions necessary to explore lots of topics. There's many things that I didn't get a chance to cover that I wanted to, such as the purely imaginary circle, the connection between the absolute imaginary elements I and J, and the introduction of Euclidean geometry from projective geometry. I want to discuss about systems of concentric circles and generalizations thereof, the imaginary sphere, and various other problems such as when do 2 conics meet in general at either real or imaginary points. I think that's a fairly interesting classification problem to be studied, as well as the issue of how one can construct elliptic projectivities which have different periods. That's actually something I've done a fair amount of research on, but have yet to publish anything about it. And this is just a mind map I made quite some time ago during learning this subject. So if you've made it this far, well done. And if you're interested in learning more about these kind of subjects and you want to answer further questions such as how do you find out the contact points of an imaginary line with a conic, or what do these imaginary elements behave like in 3-dimensional space, well, I strongly recommend a book simply called Projective Geometry by an author called G.B. Mathews. So if you Google for that, you should be able to find it online. Happy imaginary geometry.